In the last lecture, we talked a little bit about non-monotonic logics, the general category into which they fall, and then I explained why we are going to focus in particular on one type of non-monotonic logic, one that involves the use of probability theory. So here we are going to learn something about probability theory, some of its details, and a few of the central principles involved in it. So probability. Where did probability theory come from? This is a really interesting historical question because people have used the language of probability, and the notion of probability has been used in business and the gaming industry for as long as there have been businesses in gaming industries. You got to know something about odds. You have to know something about statistical charts where you can predict likelihood of disasters and things like that to figure out how much you want to charge for an insurance policy, for example. Probability theory as a mathematical theory, however, was only discovered fairly recently in the 1700s by Pascal. Pascal is most famous for his wager argument for believing in the existence of God, but he was also a fairly good mathematician and knew a bunch of other things as well. Turns out he died very young. He had converted to Catholicism, I think at about age 31, and he was dead by age 36. And what we have of his writings is primarily gathered together in Pensées, which is French for thoughts, and it's the story of Pascal's conversion, his thinking about various things, and it includes the wager argument. Pascal died because of complications from the lifestyle he lived before converting. So he drank a lot, he gambled a lot, he caroused a lot, and that led to him having a certain kind of friend and also to various diseases that led to the end of his life. One of his friends was the Chevalier de Mer, who had a gambling house. The Chevalier introduced a game into his gambling house. It involved the roll of a single six-sided die, a fair die. And the goal, if you played the game, you paid some money, and your goal was to avoid rolling a six. You would win if you avoided it 4 times in a row. Otherwise, you lose. Now, the Chevalier looked at this game and thought, this is a good game for my gambling house because we're going to win money on this game. He expected he would win 2/3 of the time. You might wonder, where did he get that number? Well, the chance of rolling a 6 on any one roll of the die is 1/6. And that means you have to avoid doing that 4 times in a row. So he said 4 times 1/6 is 2/3. And so we should win a lot of money on this game. Plus, it's kind of a fun game. Okay, so he was winning money. He wasn't winning as much as he predicted he'd be winning, but he was winning money. He then decided the game ended too quickly, so he changed the game to a game involving 2 dice rather than 1. And the goal, instead of avoiding a 6, it was to avoid rolling a 12. And he asked himself, well, how many times should we make you have to avoid rolling a 12? And he wanted the game to be symmetrical with the first game. So he tried to figure out, how do we get the same 2/3 value that I got when I predicted how much we'd win with the first game? And he thought this way, well, what's the chances of rolling a 12? You roll a 12 if you get a 6 and a 6. That's the only way to get a 12. The chance of getting the first 6 is 1/6. The chance of getting the second one is 1/6. 1/6 times 1/6 is 1/36. So we want 2/3 of that number. That would be 24. So you win if you avoid rolling a 12 24 times in a row. Now, what happened when he played this game is he went broke. He lost money, the casino shut down, and he wrote Pascal a letter. In the letter, he asked Pascal whether he had had just a string of bad luck and that's why the casino went broke, or if he made a mistake. And the answer is he made a very serious mathematical mistake in calculating his chances of winning. He miscalculated both probabilities for game 1 and game 2. Now, the simplest way to see this, look at the first game. You win if you avoid it 4 times in a row. You're the player. So if you hit a 6 anytime in the first 4 tosses, you lose. And the Chevalier thought that was enough times to give the casino a good chance of winning money. But think of changing the number from 4 to some bigger number. What if, for example, you double it? What if to win you had to avoid rolling a 6 8 times in a row? Well, then you get nonsense, because the Chevalier's practice was to say, well, you avoid rolling a 6, chance of rolling a 6 is 1/6. So if you do that 4 times, you multiply 4 times 1/6, and that gives me a 2/3 chance of winning. But now if you change it to 8, you're going to multiply 8 times 1/6, and now you get a probability of 1.25 of the house winning. Whoops, 1.33, I multiplied wrong, right? The point, though, is if you just up this number higher, you should never end up with a case where the probability is greater than 1, because that's impossible. So just by noticing that his formula for solving this problem leads to such a disaster shows you that that's not the right way to calculate the formula. Now, it turns out that this is a common error made in probabilistic reasoning. It actually occurred during the Cold War in the 1950s. Everybody's worried about Russian bombers flying in, eluding our defense networks, and dropping an atomic bomb on one of the coastal cities. So the New York Times decided to calculate the chance of our defense systems shooting down an incoming bomber that had a nuclear weapon on it. What they found out was that there are 5 layers of defense. Each of them has a 0.15 probability of shooting down a plane. It will get 15% of the planes that come through it. That's not very good, but there are 5 of them. And so the article was written with that point of view in mind. Each one is not that good, but we have 5 layers of defense. And so then they multiplied 5 times 0.15 and said, so we're pretty good. We've got a 75% chance of shooting down an incoming bomber. You can see, I hope, that this calculation device is exactly the same as that used by the Chevalier. And you can also see exactly why it has to be a crazy way to calculate things. So if you have a probability of 0.15 and you think that 5 layers of defense gets you to a 75% chance of shooting down an incoming plane, how about just build 5 more levels of defense? Now you have 10 levels of defense. And if you use the same formula, you'll multiply 0.15 times 10 to figure out the likelihood of an incoming plane being shot down. And now you end up with a probability of 1.5, which is nuts. So something went wrong. Something went wrong. What goes wrong? Well, what goes wrong is this. Go back to the initial Chevalier game. You're trying to avoid rolling a 6. So you put your money down, you pick up the dice or the die, and you roll it. Now, the chance of you getting a 6 on the first roll is 1/6. What's the chance of you getting a 6 on the second roll? You're tempted to say 1/6, but that's a mistake. It's a mistake because getting a 6 on the second roll is a complex event. You can't get to the second roll unless you avoid a 6 on the first roll. So the chance of getting a 6 on the second roll is 5/6 times 1/6. It's getting a non-6 on the first roll and then getting a 6. Same thing for the third. The third roll, the chance of getting a 6 on the third roll requires that you avoid a 6 on the first two rolls. The chance of that is 5/6 squared. And then you multiply that number times 1/6. So you can see that the more rolls you take, the less likely it is to get a 6 on that particular roll. It's a decreasing function. And that's why, no matter how many times you roll the dice, for any finite number that you roll the dice, there's still some chance of getting a 6 on the next toss. And the probability of avoiding it never exceeds 1. Okay, so that's the mistake that he made, but in the process of figuring out the mistake that the Chevalier made, Pascal discovered the probability calculus. Here's one way to present it. Now, in the Teitelbaum book, the presentation is similar to this, but not exactly the same. It's worth noticing what the differences are. But the first thing to notice is that probability is a function that generates values between 0 and 1 inclusive. Second, this is the crucial thing. Teitelbaum will emphasize to you that the additive nature of probabilities is the central feature of probability theory. So where A and B are incompatible events or propositions, the probability of A or B is just the sum of the two probabilities, the probability of A plus the probability of B. Now, it's important to be very clear on what incompatibility means here. There will be another notion, the notion of independence, that you have to keep separate, keep differentiated from incompatibility. So independence is when the probability of one event has no effect on the probability of another. Incompatibility is a different, more logical notion. Incompatibility between two events or propositions tells you that both of them cannot occur. Both of them could fail to occur, but they can't both occur. So you can't get both a 6 and a 3 on one toss of a die. You can get something other than a 6 or a 3, but the disjunction of getting a 6 or getting a 3 is a disjunction between incompatibilities. So there, all you'd have to do is add. What's the probability of getting a 6? 1/6. What's the probability of getting a 3? 1/6. So what's the probability of the disjunction? 1/3. Okay, that's the disjunction rule. It's sometimes called the restricted disjunction rule because it has a restriction. The events have to be incompatible in order for you to be able to add like this. We will also get a general disjunction rule later on that tells you what you do with disjunctions when the events aren't incompatible. But the axiom is the restricted disjunction rule, where the restriction requires that the events or propositions be incompatible. Next, now this can be formulated in different ways. So sometimes it's said where A is a tautology, its probability is 1. Sometimes it's put in the way I put it, where A is necessary, its probability is 1. Sometimes, even worse, it's put this way, where A is certain instead of necessary, its probability is 1. I think the certainty account is the most misleading. Tautology, it would be fine, but I like the language of what's necessary. So 2 + 2 = 4 is necessary. Maybe it's also a tautology, but in either case, it doesn't matter. Its probability is 1. Maybe water is identical to H2O, and that's necessary. So then its probability would be 1. Logical truths will also have a probability of 1. So if P implies both R and S, then it implies R. So the probability of that claim will be 1 as well. Next, we get a ratio formula telling us how to interpret this slash. the probability of A given B, or if you don't want to use ordinary language, just call it a slash. What's the probability of A slash B? How are we supposed to understand that? Here's the ratio formula that tells you it is the probability of the conjunction divided by the probability of the condition. B is the condition. The thing after the slash is the condition. Thing before the slash is the thing on which it is conditioned. I'm sorry, that's not the right way to say that. The thing before the slash is the proposition we're giving a probability to on this condition. So the probability of A slash B is just the division that you see here. It is the probability of the conjunction divided by the probability of the condition, provided that the probability of the condition is greater than 0. That's because division by 0 is not defined. Finally, we don't need this, we could prove this, but we're going to list it as an additional axiom. We have a rule, the second one, which tells us what to do to calculate the probability of a disjunction. Here, we have a rule that tells us how to calculate the probability of a conjunction. So the probability of A and B is the probability of A times the probability of B slash A. That is called the general conjunction rule, because notice there's no restriction on the relationships between A and B. If we want a restricted conjunction rule, we will restrict what we say to cases where A and B are independent. Now, A and B are independent when the probability of B given A is the same thing as the probability of B, without the condition at all. So for the restricted conjunction rule, if A and B are independent, then we can calculate the probability of the conjunction just by multiplying the probability of A times the probability of B. That's something we'll prove too. Here we go. The conjunction rule. The probability of A and B is the probability of the first times the probability of the second, conditional on the first. Now, suppose that the truth of B of A has no probabilistic effect at all on the occurrence of B. Then the probability of B given A is the same thing as the probability of B. So if we plug that into the rule, it becomes the probability of A and B is the probability of A times the probability of B when A and B are independent. So we now have both a general and a restricted conjunction rule. We have only a restricted disjunction rule. Let's talk about what to do when we have disjunctions that aren't incompatible. They are not exclusive of each other. So look at some examples where this might come up. What's the probability that you draw either a queen or a club from a fair deck? Well, that's not an exclusive disjunction, right? Because there is a queen of clubs. So you can't just add the two. What you can do is add and then subtract the probability that both occur. So you can say this, look, if they're not exclusive disjunctions, then we're going to add the probability of the first together with the probability of the second, and we're going to subtract from that the probability that both occur. So is the probability of drawing, here we turn to conjunction, what's the probability of drawing both a club and a queen? Is it 1/4, that's the probability of drawing a club, times 1/13, the probability of drawing a queen? Yes, because the two are independent. Drawing a queen neither raises nor lowers the probability of drawing a club. So I give this example to help you see that when you turn from a disjunction, drawing either a club or a queen, to a conjunction, drawing both a club and a queen, the language of exclusivity drops out of the picture entirely. Exclusivity applies to disjunction problems. That's what you ask about. Exclusivity does not apply to conjunction problems. Instead, what applies to conjunction problems is the notion of independence. And that should be obvious. If you think, what would it take to draw both a queen and a club out of a fair ordinary deck with no jokers in it? There are 52 such cards, and one of them is the queen of clubs. So the chances should be 1/52, and that's what you get when you multiply 1/4 times 1/13. So what can we do to prove this general disjunction rule? That when you have non-exclusive events, you add and then subtract the conjunction. Here comes the proof. Now this is going to turn out to be a recurring pattern in almost every major proof we ever use in probability theory. One thing that we're going to prove later on, we have not proved it yet, but we're going to prove that if two claims are logically equivalent, then they have exactly the same probability. Now, if you think about the relationship between A and B, you can say this: the probability of A should be the same as the sum of the probabilities of A and B and A and not B. Now, why would that be true? Why would that be true? Well, let me see if I can write this on the board and then eliminate it later. Look, A is logically equivalent to this. A and B, or A and not B. Now this is a key insight that's going to be used over and over and over again when we're doing proofs in probability theory. We're going to try to look at the A space. So you want to know something about the A space. Let this whole thing be the space. Well, one way to learn something about the A space is to cut it into parts. Let's partition it into two regions. Now, if you partition into two regions by a claim and its negation, that will exhaust the A space. That's what this disjunction says. If you've got the A space, you can cut it into parts. The part that's B and the part that's not B. So A will be logically equivalent to the disjunction of the first part or the second part. So what will be true is either A and B or A and not B, since one of the two, B or not B, is going to be true. So that or this. All right, so that's a way of partitioning the A space that's exhaustive and exclusive of each other. And so A, it turns out, will be logically equivalent to this disjunction, the disjunction of A and B or A and not B. All right, now notice as well, this disjunction is an exclusive disjunction. It's not possible for both A and B to be true and A and not B to be true, because it's not possible for B and not B to be true. So this is an exclusive disjunction, which means we can get its probability just by adding the probability of the first to the probability of the second, which is just what we have up here in this formula. On the right side of this equation, we have the summing of these two probabilities. And as long as the probability of logically equivalent claims has to be the same, the probability of A will be the same as this sum. Okay. The same is true The same is true for the second formula. The probability of B is the same as the sum of two probabilities where we partition the B space by first A and then not A. Okay. This idea of partitioning, I want to emphasize, will be crucial in almost everything that we do from here on out. So learning how to do this, learning how to see this is very important. So we partition B into the A part and the not A part, and then we disjoin those two parts. That'll be the same thing as B. The whole B space will be the part that's A together with the part that's not A. So the A and B or not A and B. And then those are exclusive disjuncts, so you can get their probability just by adding. Now, the probability of A plus B will then be the same by the logical equivalence principle as the probability of this plus the probability of this. Since the top one is logically equivalent to A and the bottom one is logically equivalent to B. So probability of A plus the probability of B is just the sum of those two equivalent claims. Now, subtract A and B from both sides. We then get the probability of A plus the probability of B minus the probability of A and B is the same as the probability of A and not B plus A and B plus not A and B. That's just simple algebra there. Remember, we had probability of A and B up here twice on the right side of our formula. Note that A or B is logically equivalent to A and not B, or A and B, or not A and not B. So those are the only three ways, the precise three ways in which A or B is true. Either the first one is true, together with either the truth or falsity of the second, or the first one's false, but the second one's true. The only way in which this turns out false is when you have not A together with not B. Now, by the way, this formula is called, let me write this on here because this is a notion that's going to come back up later. This is called the disjunctive normal form. Actually, let me try something different here. I think there's a way to do this without being so ugly. Let me see if I can just type this. Very nice. Okay. This highlighted formula is called the disjunctive normal form of A or B. Here's a fact that we are going to learn and actually prove. For every proposition, no matter what it is, has a logically equivalent disjunctive normal form. The way you find it is you build the long truth table for the formula you've got, and then you pick out the lines on the truth table under which that proposition comes out true, and then you disjoin them. When you disjoin each of the lines on the long truth table where the formula gets evaluated as true, you then have the disjunctive normal form of your original proposition. Okay, now notice each of these three disjuncts of the disjunctive normal form are also exclusive of each other. At most, only one of them could be true. So you can get the probability of this big disjunction just by adding the three together. And notice that's just what the right side of this equation is. So we can now replace the right side of the equation with the probability of A or B here, which is what we do. And that completes our proof of the general disjunction rule. It completes the proof provided logically equivalent propositions have the same probability. I've asserted that, but we haven't proven it yet. So let's do that. Anyway, that's the first very important proof. The general disjunction rule tells you what to do with the disjunctions when the events or propositions in question are not exclusive of each other. So here's our logical equivalence claim. We're going to assume that A and B are logically equivalent. Now, if they are, it will be a theorem that not A or B is true. Why is that going to be a theorem? Well, I'm going to simplify a little bit, but let's do this. Take this formula and apply the wedge arrow rule, and you end up with A arrow B as a theorem. And by the deduction theorem, if you can derive B from A, then you can prove A arrow B from no premises whatsoever, which is what this claim, if it will let me highlight it, what that claim says. That claim says A arrow B is provable from no information at all. That's on the assumption, of course, that A is logically equivalent to B. Okay, so that's the first step of our proof. By the assumption, this disjunction is exclusive, this one, not A or B, because it's impossible for A to be false and B be true. So its probability is the probability of not A plus the probability of B. That's the restricted disjunction rule. That's one of our initial axioms. Now, since the disjunction is necessary, it's necessary because it's provable from no premises whatsoever, its sum is 1. That was another one of our axioms. So the probability of B is going to be 1 minus the probability of A by just subtracting the probability of not A from each side. Now, so long as the probability of X is the same thing as the probability of not X, we then get the probability of B is 1 minus the probability of not A, which is the same thing as 1 minus 1 minus the probability of A. That's assuming this, what's called the negation rule. We replace the probability of not A with 1 minus the probability of its opposite. And 1 minus 1 minus the probability of A just is the probability of A. So we simplify to the probability of B just is the probability of A. We assumed logical equivalence and we derived same probability. That's the logical equivalence claim. Now, notice that that proof relied on a negation rule, which we have not proven. So let's take a look at how to prove the negation rule. The negation rule tells us that the probability of a claim is 1 minus the probability of its denial. Now notice that A or not A is the logical truth. It's hence necessary and thus has a probability of 1. Notice as well that the disjunction of A or not A is an exclusive disjunction, so you can get its probability just by adding. So the probability of A plus the probability of not A is 1. And then simply subtracting the probability of not A from each side, we get the probability of A is the same thing as the probability of not A. All right, that's some of the basic rules. There are some others in the textbook, in the title-bound textbook, that we are going to look at and work on proving as well. There's a bunch in the homework problems. And this is something that I will send a separate note around about, but I anticipate the take-home final for the third part of the course will be, in large part, some of the homework problems from the title-bound book. So that means if you want to get ready for the take-home final, pay attention to the title-bound homework. You still will need to make attempts at all of the homework problems to be uploaded to Canvas for that part of your grade, but the take-home final will require you to be able to succeed at those homework problems and not merely try. Okay, some things about conditional probability. First, remember the definition of the slash. The probability of A slash B is the probability of A and B divided by the probability of B, provided that the probability of B is greater than 0. So let's talk a little bit about some examples here. What's the probability of rolling a 6 given that you've rolled an even number? Well, that's the probability of rolling both an even number and a 6 divided by the probability of rolling an even number. What's the probability of rolling a 6 and an even number? Well, in this case, you can resort to calculating it by the ratio formula, as this is called, or you can merely count. One way to do it is just say, well, the condition is rolling an even number. There are 3 of those. One of those is a 6, so the probability should turn out to be 1/3. Well, suppose you use the ratio formula. The denominator is going to be 1/3. What is the numerator? What's the probability of rolling both a 6 and an even number? Well, the math here is not that hard to figure out, but let's do it. If you've got a big division problem with 1/3 at the bottom, and you know that the answer is going to be 1/3, what you're doing is trying to calculate what the probability of X is and have that calculation make sense to you. So the probability of A and B should be shall we say 1/6? Because the probability of rolling a 6 and an even number is just the same thing as the probability of rolling a 6. Are y'all happy with that? That that's the value of X? I hope you're not. I did it to make you pay attention to the numbers, hoping that it would work, because look at what happens. If you put 1/6 over here, what is 1/6 divided by 1/3? It is 1/6 times 3/1, which gives us not 1/3, but 1/2. So we did something wrong. What did we do wrong? Well, what we did wrong was we took the probability of the conjunction. Let me clear this off because it's mistaken. We wanted to calculate the probability of A and B. And what we did was we just said, well, that's 1/6. But we're supposed to do, what's the probability of the first? Probability of rolling a 6 is 1/6 times, what's the probability of rolling an even number, given that you rolled a 6. Probability of an even number given that you rolled a 6 is 1. Correct? There are 3 of these. Whoops, there's 1 of these because A is 6, right? A is 6, and 6 is by definition even. All right, now what if we switched it around the other way? Suppose we start with B. What's the probability of B and A? Well, the probability of an even number is 1/3. And what's the probability of A given B? Well, remember B was, whoops, I'm sorry. I'm getting numbers all confused. Let me, I apologize. Let's clear this off. The probability of getting an even number is not 1/3. It's 1/2. So let's start over with the problem. We start and we count and we say the probability of getting both a 6, given that you rolled an even number, should be 1/3 because there are 3 even numbers and one of them is a 6. So what's the probability of getting an even number? It's not 1/3, it's 1/2. And so some number X, if I had done this right the first time, we would have finished this long ago. There is some number that goes up here so that that number divided by 1/2 gives us 1/3, and that one is 1/6. So if I hadn't put the wrong denominator in the first time, we would have already seen the correct solution. And we already saw where we can get that 1/6. You can just count. What does it take to get both a 6 and an even number? Well, that's the same thing as getting a 6, because a 6 is an even number. And you could calculate it the long way by going the probability of A times the probability of B given A, but the probability of B given A would be 1. So it's just going to be the probability of A, the probability of rolling a 6. Okay, so we can calculate conditional probabilities that way. Here's the second case. What's the probability of drawing 2 aces in a row? Now here, you want to be careful because you need to be told whether you are replacing the first card you draw before you draw the second card. If you don't take that into account, you can't determine whether or not the 2 events are independent. So if you replace the card after drawing it, then you have independent events. Probability of drawing an ace is 1/13 if you replace it. The probability of drawing it the second time, or another ace the second time, is 1/13, so we get 1/169. If we don't have independence, then we have still the probability of drawing the first ace is 1/13, and we're going to multiply that times the probability of drawing an ace the second time, given that you got an ace on the first one, and we didn't replace this time. So there's 51 cards left, and only 3 of them are aces. So without replacement, the probability would be 1/13 times 3/51. A final example that we can talk about is the gambling house case, where the probability of rolling a 6 on the second toss is not the same thing as rolling, same probability as that of rolling a 6 on the first toss. The first one is 1/6, the second one is a complex event, avoiding a 6 on the first and getting a 6 on the second. All right, Now, this total probability theorem will be important to us. If you remember, when I was proving the general disjunction rule, when I proved the general disjunction rule, I drew a space for A, and then I partitioned it into parts. Now, the easiest way to partition is just in terms of one claim and its negation. But you can partition however you wish. That's a partition that creates 1, 2, 3, 4, 5, 6, 7 subregions. What's important is that there's no overlap between any of the regions you've created. That will guarantee that they're all exclusive of each other. This little region is exclusive of all the others, and the same is true of the remainder. So partition however you want. We define a partition as a way of carving up the space in question that's exclusive and exhaustive. In other words, it covers absolutely everything in the big box you started with, and it does it in a way that rules out overlaps between any of the regions. So partition. Partition a space, and let's call those individual partitions events A1 through AN. They will be mutually exclusive, and their sum will sum to 1 because they're exhaustive of the space. So we want both the partition to be exclusive and exhaustive. Then we can calculate the probability of the space itself, which in this case we're calling B. Let B be the space that we partition however many ways we wish by the A's, and there are n of them. Then what you do is you sum this product from 1 to n. You sum the probability of B for each individual partition times the probability of the partition itself. So the first number just says, well, you take B and this region, B given that region. What's the probability of B given that region? What's the probability of B given that one, that one, that one, that one, that one, and that one? Okay, now we've exhausted all of the conditional probabilities, but there's something we haven't taken into account of. We haven't taken into account the size of each of these partitions. Notice this partition is pretty big. This is biggest of all. This one's tiny. In order to do the summing properly, you have to multiply the conditional probability of B given a partition times the size of the partition. That will be the probability, how much of this total space that particular partition occupies. So this one is going to be a much bigger probability than this. But remember, the summing of all of these probabilities sums to 1 because the partition is exhaustive. That's the total probability theorem. The conditional probabilities on each part of the partition times the size of the partition itself. Sum all of that, and that will give us the probability of B. Another formula that's going to turn out to be really crucial to our confirmation theory is Bayes' theorem. So here are 3 different versions. The original Bayes' theorem is just this. The probability of a hypothesis given the evidence is the reverse probability. Some people call this the likelihood of H on the evidence. That's very misleading to me, so I try not to use that language. This is the probability of the evidence on the hypothesis times the probability of the hypothesis divided by the probability of the evidence. Some people call this part everything except the reverse probability, the probability of H over the probability of E. Some people call that the Bayes factor. Other people call other things the Bayes factor. But if you call it the Bayes factor, then what it tells you is that the probability of H given E is a function of two things, the reverse probability and the Bayes factor. The Bayes factor is just the probability of the hypothesis divided by the probability of the condition or the evidence. We are going to prove Bayes' theorem, but one thing to note is that Bayes' theorem has an expanded version that I want to call your attention to. It helps connect it with the total probability theorem that we just talked about. Notice the difference is the denominator is much more complex in the expanded form. Up here, we just had the probability of E. Down here, we've got an ugly mess. So what's the connection between what's down here and what's up here? The answer is, let me do this. The answer is the central idea that we use to prove logical equivalence. E is equivalent to E and H, or E and not H. So remember, I drew a box. I was using A and B at the time. I drew a box for A, and then I partitioned that box into two parts, the B part and the not B part. So that's all we're doing here. Partition E into two parts, the part where the hypothesis is true, the part where the hypothesis is false. All right, now that disjunction is exclusive. So if you look up here, I'm just going to leave this for a moment and get out of it. If you look up here, the denominator is now a sum. That's because what we're doing is calculating the probability of a disjunction. We are replacing the probability of E with the probability of an equivalent claim, which is E and H or E and not H. Since that's an exclusive disjunction, we get to just add. Now, what's the probability of E and H? Well, that's the same thing as the probability of H and E, since those two claims are equivalent. And notice what we're doing. We take the probability of H and multiply it times the probability of E given H. That's just the conditional probability rule, the general conjunction rule. The probability of a conjunction, A and B, is the probability of A times the probability of B given A. So I replace this conjunction with the probability that the general conjunction rule tells us to use, and then I do the same thing on this side. I flipped each of these conjunctions around so that the H element came first, and then I take the unconditional probability of H, not H on this side, H on this side, and multiply it by the conditional probability of the second conjunct given the first conjunct. Okay, so that's the expanded form. And notice once you see that and once you appreciate the total probability theorem, we could replace the denominator with something as long and complicated as we want, because we got this particular one by partitioning the E space in terms of H and not H, but we could partition it in terms of however many parts we wanted. If we had 17 of them, then we'd have a disjunction with 17 separate parts. And each of the parts would be exclusive of each other and exhaustive of the E space. So we could take the conditional probability times the size of the partition plus the conditional probability times the size of the partition for all 17, and you could have that for a big complicated denominator if you want. But it turns out this one where we just partition the evidence space in terms of the hypothesis is most useful for helping us apply Bayes' theorem to particular cases. So the proof of Bayes' theorem is stunningly simple. In fact, it's so simple you wonder, why does it get named after Thomas Bayes at all. It's so simple. The reason is because it's incredibly useful. There are other things like this in the history of mathematics where the proof or the idea is incredibly simple, but incredibly useful as well. The most famous in the 20th century is Nash equilibria points, which turns out to be found in game theory. And Nash equilibria points is an incredibly simple idea, but it's been useful in so many domains that Nash is one of the most cited mathematicians in the 20th century because of this. In any case, we start out with the simple conditional probability definition. The probability of H given E is just the probability of the conjunction divided by the probability of the condition. Now, H and E is logically equivalent to E and H, and so the probability of this last conjunction, the one in the numerator, is the probability of H times the probability of E given H. So the probability of H given E is the probability of E given H times the probability of H over the probability of E. And notice that is just the simple version of the Bayes rule. If you want the expanded denominator, you then apply the logical equivalence principle to get that the probability of E will be the same thing as the probability of E and H or E and not H. And then you get the expanded form that way. Okay, let's do one quick application of Bayes' theorem to finish up our initial discussion of probability. We start out wanting to know what the probability is of a hypothesis given a body of evidence. Bayes' theorem tells us that we can calculate this if we know the probability of the hypothesis independent of the evidence, the probability of the evidence, and the probability of the evidence on the hypothesis. Those are the three elements in Bayes' theorem. So here's a simple example. Take a medical test for a rare disease. Your doctor tells you, I think you should take this test. And suppose we already know that 1 in 1,000 have the disease, that the test gives a false positive 5% of the time, but never fails to detect the disease if it's present. So notice what we're doing is we want to know, this is called the base rate. The base rate is the probability of the hypothesis independent of the evidence. So we want to know the base rate. That gives us the probability of the hypothesis. We also want to know the false positive rate and the false negative rate. We'll see how to plug that into Bayes' theorem in just a second. So you take the test and the test is positive. How likely is it that you have the disease? Now, why would we want to know the false positive and false negative rates? Well, if you remember in the expanded form of Bayes' theorem, we had the probability of the evidence given the hypothesis and the probability of the evidence given the failure of the hypothesis. All right, so suppose you get a false test. What's the probability of getting a false test given that you have the disease? What's the probability of getting the evidence that you have the disease given that you in fact have it? What's the probability of getting the evidence that you have the disease given that you don't have the disease? One of these is the false positive, one is the false negative. Okay, and if we know both the false positive and the false negative, that one and that one, and we know the probability of the hypothesis, we can figure out what the probability of the denial of the hypothesis is, and now we have all of the elements that we need to calculate the probability that you have the disease given a positive test on the sample that you provided, okay? All we need is false positive, false negative, and base rate. Okay, the answer then can be computed using Bayes' theorem. We know that the probability of the evidence given that you have the disease is 1, right? Now, having the disease is the H thing. So the probability of E given H is 1. The evidence, remember, is the test came back positive. The test says you have the disease. Okay, so we know that the probability of that evidence, given that you have the disease, is 1. We know that because we said the false negative rate is 0. It never fails to detect the disease if it's present. Okay, we also know that the probability of the hypothesis independent of the evidence, that's 0, 0, 1. Where do we get that? 1 in 1,000 have the disease. Okay, so the probability that you have the disease prior to and independent of taking the test is 0.001. If we multiply these numbers and divide by the probability of the evidence, we have an answer. So what is the answer? The probability of the evidence is the sum of the following. We partition the evidence space into the H part and the not H part. Then we add the two parts together, multiplying the false positive rate we multiply the false positive rate by the size of the not H space, and then we multiply the false negative rate times the size of the H region, the H part of the E region. That gives us the expanded denominator for Bayes' theorem. Now we know that the false positive rate is 0.05, 5% of the time. We know the probability of not H is 0.99. We know the false negative rate is 0. So the probability of the evidence given the hypothesis is 1, and we know the probability of the hypothesis itself is 0.001. So the probability of the evidence, you can calculate this for yourself, but the probability of the evidence, the denominator for Bayes' theorem, is 0.05095. Now plug that into Bayes' theorem with the rest of the calculation, and the probability that you have the disease given the positive test is about 0.02, which makes you wonder why you put so much confidence in the test in the first place. If you got a positive test, you'd be inclined to panic or at least worry. But one positive test by itself, if this is all you know about the case, doesn't give you strong enough reason to get that concerned. Now, it's a very powerful test. There are ways to measure the power of the test, but notice the probability went from 0.001 to about 0.02. That's an increase of 20 times the probability. That's a pretty powerful increase in the probability. But if you're just thinking, should I conclude that I now have the disease? The answer is that the probability is very low that you have the disease. We will look at cases in the Teitelbaum homework about what happens if you're able to take a second test. One of the things doctors do is recommend a second opinion. And part of the reason for that is if you run an independent second test, you can calculate how much more the probability will rise and how many more tests you would need to go through in order to make it more likely than not that you have the disease.